Jai Hind everyone. Today my topic of discussion is pumping lemma. So pumping lemma for regular language, and as we know that pumping lemma can be used for context free language and also for regular language. So I am going to discuss pumping lemma for regular language, and in subsequent lecture I will discuss pumping lemma for context free language. So what is regular language? So any language L is said to be regular if there exists a regular expression over sigma such that L is accepted, L is equal to LR. So a language, any language L is going to be regular if we can get regular expression, or equivalently we can get any DFA which can accept the language. So or we can get any other regular grammar which can accept the language, right? So if a language is regular, if any language L is regular, so there are three things to show. Number one, you can design a DFA, right, which can accept this particular language, or number two, you can give a regular grammar type 3 grammar corresponding to particular language, or you can design a regular expression which can accept the language, right? So this is about regularity. So what about a language which is not regular? So pumping lemma will be used to show that if a language is not regular. For regularity, you just design DFA or design regular grammar or design regular expression. For example, if question is coming like so that this is a regular. So if this is the question a to the power 2n, so that this is a regular grammar, a regular set or regular language. So it is easy that you just design a regular expression n minus 1 because n is greater than or equal to 1. So regular expression can be this, or equivalently you can design like this n minus 1 then a. This is also the same regular expression for a particular language. So regular expression for this is a, then a is star and a. So question is that this is regular, so just design a DFA for this. So if you we can see that this is the DFA corresponding to particular language. See, this is A, right, and then this is Q1 and this is Q2. Let's say this is A and then this is A, right, A and then this is A. This is number 3, Q3, right? So this is actually the answer. So this is NFA. We can see that this is NFA, and this NFA can be converted into equivalent DFA. So this we can design a particular DFA for this language because this is NFA. We can design DFA. So let's discuss application of this pumping lemma. So number one application of this pumping lemma is that this can be used to show language is not regular, non-regular. Regularity is not a problem. You can design DFA, or you can give regular grammar, or you can write regular expression. But pumping lemma is very useful to say if language is not regular. For example, if we talk about language like AN, BN, n greater than or equal to 1, this language is not regular, you know. We cannot design DFA for this language, and so there are many ways to check whether it is not regular or not. We can design a context free grammar ASA or AB. This is a context free grammar, type 2 grammar for this type 2 grammar. If question is coming like so that this is not regular using pumping lemma, so we can follow the pumping lemma for this task. So what is the statement of this pumping lemma? Pumping lemma for regular language. So suppose this is a DFA, Q sigma delta Q0F, be a finite state with n state, because this is finite state automata. So assume that this is having n number of states, right? and let L be a regular language accepted by this. Since L is regular language, that means it is going to be accepted by some finite automata, and assume that finite automata has n number of states, right? So what is hypothesis of this pumping lemma? If for any W belong to L with length of W greater than or equal to number of state in DFA, right? So if any W belong to L such that length of W is greater than or equal to number of state in DFA, if this is the situation, then W will be divided into three parts, X, Y, Z, right? This is the statement, in such a way that length of Y greater than or equal to 1. This part minimum length should be 1. Clear? Okay. And this is the one restriction, and length of the beginning, length of xy less than or equal to this number of state in DFA. This is second restriction, number one restriction. Number two, if this is the situation, then x y to the power I z will be part of language for every I greater than or equal to 0. This means that we will get xz, xyz is already there, xy square z up to and so on. This all belong to language, particular language. That means there are infinite word which can be generated by this language. So all will be part of the language. Clear? So okay. So how to prove it? That yes, how to prove it? So let us understand the proving. Okay, so this is the situation that if length of W greater than or equal to n, if this is the situation, right, then W will be written as part of 3 string with length of y greater than or equal to 1, length of x y less than or equal to n, and x y to the power I z belong to L for every I greater than 0. So proving is very easy. So suppose that okay, so let suppose that W is A1, A2 up to and so on AM. Suppose this is the W, right? And with restriction on W is that on M is greater than or equal to N. Right? So M is greater than or equal to N. This is minimum N. What is N? N is the number of state in accepting DFA. Clear? So now here hypothesis gets satisfied. Length of W is M, and since M is greater than or equal to N, this is true. This is true. That means hypothesis is satisfied. So now this will be divided into three parts, right? And so suppose now this is going to be divided into A1, A2, and let's say AI, right? And then AI plus 1 and AJ, and next is AJ plus 1 to AM, right? This string can be written like this. We assume that this is X, this is Y, and this is Z. Okay, so since we have n number of states which are unique states, and this string is more than this, right? This string is more than number of states. So this means that there are two indices, let's say I and J. By pigeonhole principle, there is index I and J such that Qi equal to Qj. It's clear? Qi equal to Qj. Why? Because this string is length, its length is less M, and M is greater than or equal to N. So we have N states. N state, let's say Q0, Qm, and M is minimum N. So how many states do we have? how many states do we have? We have minimum m plus 1 state, right? Q0, Qm, and m is minimum n. So this is n plus 1. Total n plus 1 states we have now. So that means you will get any two states. Let's say I and j, such that its index is less than j, I less than j, such that this qi is equal to qj. That means yes, there are two states which are equal. So if you just divide like this, see this. So yeah, if you just divide like this, see, and this is our q0, right? And this is qi equal to qj, and then this is qm. Qm is the final state, right? And this is x, a1, a2, ai, and there is pumping on ai plus 1 to aj, and this is y, right? And this is aj plus 1 to am. This is the string. Minimum m is n. Minimum m is n. So two states are going to be equal, right? And we know that this delta q, if you start from q0, let's say a0 up to and so on ai, let us define this as qi, right? Let us define this delta as qi. So what will happen? What will happen if delta cap you are applying for, let's say, q0 and I equal to 0. So for I equal to 0, you will get xz, x and z. X is what? A1 to ai, and z is aj plus 1 to am. aj plus 1 to am, right? Yes. So now since this is equal to ai, qi, so this become qi, and then aj plus 1 to am. And we know that ai equal qi equal to qj. So qi, this become qj. So this is qj, aj plus 1, right? And am. Okay. So this is going to be qm. That means it is final state. So that means xz belong to L. It is okay. In this process, if we think about this, whether it is satisfied or not. So if you just see this, length of y is j minus I. This length of y and j minus I is minimum 1. So this gets satisfied. Length of xy, so length of xy is less than or equal to length of xyg, and length of xyz is n, right? So actually, if you see this here, length of xy is also less than or equal to n. So this for I equal to 0 is okay. Similarly, we can also check xy square z belong to L. Just like, yeah, we can also check like this is also part of the language. So pumping lemma proof is very easy. Okay. So what are the pumping lemma? As I told you that yes, this is like used to show a language which is not regular. So we are going to use the contradiction approach, right? So let us have one example. Then see this question is that in L so that this is not regular. Suppose L equal to an bn, n is not regular. You remember, this n is not same as number of state in DFA. This question can be given like am, bm, and m greater than or equal to 1. We can also give question like this. There is no problem. So how to solve it using pumping lemma? So we take any word of this language. Right? So let us take any word of this language. Take w equal to an bn. Remember, this n is index. So this can be written like ai bi and I greater than or equal to 1. This can also be written like this. There is no problem. But what we are going to get, w equal to this, right? Take w. Now here n can be taken as number of states in DFA. This is n now. This is n number of states in DFA. So now satisfy the pumping lemma. Now length of w is 2n, right? Here length of w is 2n. So this is greater than n. Yes. So that means hypothesis gets satisfied. So what will happen? By pumping lemma, we will divide it into 3 parts, x, y, z, right? And length of middle is greater than or equal to 1 and length of beginning is less than or equal to number of state. And if this is true, then what will happen? X, Y, I, Z belong to L for every I greater than or equal to 0. This is the fact actually. Clear, class? Okay. So what we are going to assume that on the contrary, this is regular. If this is the regular, then we are taking W and then divided into parts, right? So what can be the I? What can be I? Here, if we take W equal to AN, BN, right? So I can be like here Y can be A to the power K, where K greater than or equal to 1. Let's see. Y is string of A or Y is string of B only, and this K greater than or equal to 1. Or Y can be AKBL, where K and L greater than or equal to 1, right? Yes. So this is the case number 1, this case number 2, this is case number 3. We'll see that only case number 1 is going to be applicable, not case 2, not case 3. Reason behind is that because once we divide into 3 parts, we have to take care of this also, and we have to take care of the beginning too, length of xy less than or equal to n. So, right? So, let us assume that y is a to the power k. So, let us assume case number 1, y is a to the power k. So, what will happen? W is a n minus k and then a k and bn. This is okay. This is perfect division, right? Or we can say that this is a k and then a n minus k and bn. This is also possible, right? Yes. So both cases are possible. Okay. So you know here we assume that this y is a to the power k and k is minimum 1. So here length of y is k and this greater than or equal to 1. So this gets satisfied. Okay. So now you see here length of xy. If you choose y is this, so x will be this and this will be g, right? This can be the possibility. If we choose y here, so this can be lambda x and this can be z. This can be g. Both possible, both cases are possible. If we choose this division, so what will be the length of xy? Length of xy will be n, which is less than or equal to n. So that means this is also perfectly valid. This is also perfectly valid. Length of xy less than or equal to n. Okay. So that, and if you choose this also, so what is length of xy here? Length of xy is k. K of course greater than or equal to 1, but this is also less than or equal to n. Why? Because length of y is actually less than or equal to length of xy and this should be less than or equal to n. So lower limit on y is 1 and what is upper limit? Upper limit is n. Clear? So now this is clear that you can divide either with this way or you can divide with this way. So now you see here, so how to like contradict by pumping lemma? How to contradict by pumping lemma? If you divide by this, so this is x, this is y, this is z. So you know for I equal to 0, let's take I equal to 0. So if you take I equal to 0, this will be cancelled out, right? So what will be answer? W will be an minus k and then bn, and this is not part of the language. Why? This is not part of the language because in this language number of A is same as number of B, right? So but here number of A become less than number of B. So that means this is contradicting the pumping lemma. So hence case 1 is contradicting. Some textbook they will also say that y is b to the power k. Let us understand why y is not b to the power k. Let's understand. So you know, if w is an bn, right? Suppose if w is an bn and we assume that y is b to the power k, we can take like this, no problem. So this can be divided an and then bk and bn minus k, right? We can divide like an, bn and then bn minus k, right? So this is your y and this is x and this is z. But this division is not possible because y length greater than or equal to 1. Yes, it's okay. Length of y is greater than or equal to 1. This is perfectly valid, right? But length of xy, if you choose here length of xy, if you choose length of xy, this is basically n plus k, right class? This is n plus k, which is not less than or equal to n. This is not less than or equal to n. Why? Because k is minimum 1. So this case is not possible. So that's why I said that case 2 is not working. Case 2 will not be valid in this situation. So some textbooks they are saying that case 2 is valid, but we should not worry about case 2 since there is contradiction in case 1. We can say that by pumping lemma L is not regular. And what about case number 3? Same situation, case 3 is also not working. If you divide y is an bn, so this is n minus k and then akbl, right? And then bn minus l. Same thing. Here is y and this is x and this is g, right? Yes. If you see here, so there is no problem. Length of y, you know, length of y since k and l greater than or equal to 1. So length of y is greater than or equal to 1. This gets satisfied, but this is not going to be satisfied. Why? Because length of xy here, if you see length of xy is n plus l, which is not less than or equal to n. Which is not less than or equal to n. So that means case 3 is also not possible. So in this situation, contradiction is coming on case 1 and case 2 and case 3 divisions are not possible. So this is the correct explanation. So we should not go on case 2 and case 3. Some books are saying, but we should not worry about that. Case 1 is more than sufficient. So, you know, in pumping lemma, 3 different type of questions can be asked. One is like any combination of A and B. See, A and Bn. So, similarly, another question can also be asked W equal to A and Bn. See, if I am asked like C, suppose question is so that L is A and Bn, L equal to WW. Suppose this is the question, W belong to AB star. So, how to prove it using pumping lemma? How to prove it using pumping lemma? See. So, I am coming to here that WW, right? W is actually part of A and B star. So, we assume that L is regular. Question will be saying that, okay, how to prove L is not regular. We assume that L is regular, see, and take n as number of states in accepting DFA, right? So, we are going to take any word which is part of this language, see. So, take any word which is part of this language. So, you know, this can be the part A and B N. You check an, w is an, bn, so this can also be an, bn. What is beauty of this? What is beauty of this? Its beauty is that all a, b, same thing repeated. So let us understand that, okay, let's say length of w dash. On the contrary, suppose L is regular. So length of w dash will be 4n. Yes. And definitely this is greater than n. So now pumping lemma gets satisfied. So length of w dash is 4n greater than n. So this means w dash is going to be divided into 3 components, right? With length of middle is greater than 1 and length of the beginning x, y less than or equal to n and x, y to the power I z belong to L for every I greater than 0. So this is the situation. Okay. So same thing, y, if you are dividing, so y is only a to the power k, which is going to work as I explained earlier, and k greater than or equal to 1. We can say y is b to the power k or akbl, but all these cases they are not going to work, right? So now w dash you can say an minus k, then ak and bn and then an bn, right? So now if you think over it, this is the same division, an bn, this is same division, this is the same division, right? So an bn, clear? So you see here, if you just think this is x and this is y and this is z, and again for I equal to 0, for I equal to 0, you just eliminate it and you will see that an minus k, bn, this is not part of the language. This is not part of the language. Reason is very simple, because k greater than or equal to 1. So it is not following the pattern that same w, This here, this is different, and this is different. So that means this is not part of the language, hence it is a contradiction, right? So we'll continue with another questions in future. So keep watching the next video, and here are the references. You can follow this: John Hopcroft, KLP Misra and Peter Lynch. Thank you.